This video goes over 4 problems from one-dimensional kinematics, i.e. motion along a straight line. 2 of the problems are ones you might expect to see in class. The last 2 extend the ideas but use the concept of just what is the definition of velocity and what is the definition of acceleration. Let's get started. Here's the problem. We have a steel ball that was dropped from above the window. It falls and it passes the top of the window, and after some period of known time, it passes the bottom of the window. The question is, how far above the top of the window was the ball dropped? Since it's a steel ball, we should assume that there is no air resistance. This is a silly assumption, but it is often required as part of these types of problems. Pretty much everything is related to the fact that the acceleration is constant. Therefore, we can use those equations for constant acceleration, in this case, in the vertical direction. We essentially need to know something about its time, the initial position, the initial velocity, and of course the acceleration. So we can write the equation essentially for the top of this position as y of t is a function of the fact that it was dropped and it fell for some period of time, which is unknown, at some height, which we don't know, starting with a velocity of 0 and accelerating with a value of negative g, meaning acceleration in the negative direction downwards. Let's make some assumption, because we can assign it that the bottom of the window is at position 0, therefore the top of the window is at position h, and we're interested in the height above h. Applying for the same idea at the bottom of the window, it reaches the bottom of the window at some time t plus an additional time, assuming the same initial situations. We're now in a situation of 2 equations and 2 unknowns. 2 equations are equation 1 and equation 2. The unknowns are we don't know where the ball was dropped and we don't know how long the ball had been traveling. But we have enough information to solve for those values. Solving the 2 equations for the 2 unknowns, we find the time it reaches the top of the window and the height of the window relative to the bottom of the window. Consequently, the height above the window is where y0 is from the solutions minus the top because the bottom is at 0. And this is the expression that we can return. Notice it is a positive expression regardless what the value of t and h are. What is the value assuming it passes by the 1.1 meter window in 0.2 seconds? Well, we need to evaluate that value for which g is 9.8, the height of the window is 1.1, and delta t is 0.2, and it turns out our window is just a bit more than 1 meter high. Here's our second problem. This involves a one-dimensional problem, the motion along the horizontal direction. You have a speeding vehicle that has passed a California Highway Patrol motorcycle, and after some time, the motorcycle takes off and accelerates at a constant acceleration. The speeding car does not vary its speed during this process. The reason I don't use numbers here is it allows us to determine how much the time delay, how much the acceleration, and how much the speed of the car affect the time at which it takes for the motorcycle to catch up to the speeding car and how far away the speeding car is when the motorcycle catches it. We apply the same kinematic equation involving a constant acceleration, whether it applies to the CHP vehicle or whether it applies to the speeding motorist. Position is a function of time, the initial position, the initial velocity, and whatever acceleration there is. Therefore, the speeding car, since it starts passing the CHP at location x equals 0 with some speed and having no acceleration, that's its position as a function of time. However, the CHP vehicle leaves not at t, but some delayed time by delta t, again starting at the initial position with no initial speed and accelerating with some acceleration ACHP. Notice I've not actually solved these problems. I haven't even gone into a strategy. All I know is I want to know something about position. The question becomes, at what time is this position is equal to that position? That's a solved problem. The solved problem is simple. Set this equation equal to that equation and solve for t. Notice we get two answers. One is negative, one is positive. We obviously choose the positive answer, and that is the answer for the time it takes the CHP to catch the speeding motorist. It involves the acceleration of the CHP and the time delay, which adds to the time in addition to the speed of this motorist. Part B is pretty straightforward. Now that you know the time, apply the same formula. We'll use it for the speeding motorist and determine the location the speeding motorist was when he was caught. Again, we get an answer involving the acceleration of the CHP and the fact that there was a time delay, along with the fact that there was a speed for the speeding motorist. In the third problem, we are more realistic about the acceleration of the CHP vehicle. There is a maximum speed at which the motorcycle can travel, and therefore the acceleration diminishes as the motorcycle gets faster and faster. Let's use this fact to determine what is the time it takes to catch the speeding motorist and the position. So we write out our expression. We note the fact that the acceleration is not constant with time and in fact depends upon the velocity of the CHP officer. Therefore, we cannot use the same kinematic equations that you might have been required to memorize as part of one-dimensional kinematics. We have to return to the definition of acceleration and velocity. And here they are. Velocity is the time rate of change of position. Acceleration is the time rate of change of velocity. We know the CHP starts at time t equals 0 at location 0. The velocity of CHP officer is at t equals 0, also 0. From these two rate equations or differential equations, we have to solve differentially both the equations and the two initial conditions for the unknown functions. We will extract the solution and make a function of it, noting that time has been delayed by delta t. The function of the speeding vehicle is still the same, velocity times time. In the end, the goal is the same. When is the position of the speeding vehicle that of the CHP officer? This looks like an incredibly complicated answer, and that's true because it uses the Lambert W function. Once we put some numbers in, it will make sense. Where does this catch occur? The catch occurs at that same time for the speeding vehicle. And now we can apply the values. These are a bunch of parameters, a bunch of constants that we're all given. Therefore, we're going to evaluate both this time and this time, which are not functions but expressions, given the set of parameters. It turns out it takes 16.3 seconds after 587 meters. The last problem is numerically based. Normally, it is beyond the scope of introductory physics classes, but the principle is the same, therefore it should be in your class. We have an acceleration that varies with time, which depends upon position and velocity. We're going to start this object at some height h with some initial speed of 0, and we're interested in its position as a function of time. We cannot use the equations for constant acceleration, so we have to return to the definition of velocity and the definition of acceleration. We have to define what the acceleration is, and we have to include the initial conditions. Let's see if we can solve these two differential equations, v and the one for a, knowing that a is this expression with the two initial conditions for its initial position and velocity. No luck. Since we can't solve problem A, let's go to part B, which says, here's some constants that we could put into our problem. Can we figure out what's going on numerically? So let's include this constants as defining each constant by colon equals, and differentially solve the same equations with the same initial conditions, but numerically and outputting as a list procedure. Enter, enter, and you can see the procedures for both the position and velocity as a function of time. We extract out both the position and velocities as function of time solutions, so these are functions of t. Now we're in a position to answer the question, at what point does the position equal 100 meters? T100 is solving the following question. where f's solution as a function of t equals 100, we're going to do this floating point. So this is f solve. We're going to give it some range to look for, and maybe there are multiple solutions. No, all we need is this solution. How fast is the object moving at that location? That's the velocity at time t equals 100. Let's plot everything between 0 and that time. We can do it two ways. We can make an array plot, which is a plot, in this case, of 2 rows by 1 column of the position and the velocity versus time. We're going to display this array. There's the position versus time, and there's the velocity versus time. And again, not surprisingly, when it reaches the minimum amount, it's minus 74. Alternatively, we can plot both the position and velocity on a dual axis plot. And again, position versus time on this axis, velocity versus the same time on this axis. The document lays out all the problems, probably a little more slowly than I did in this video. I also include a link to the instructional video which explains why there's really only 2 equations relative to 1D kinematics. The next video will be on 2D and 3D kinematics.